where does electrical energy consumption matter? You have some examples on the slide, so if I tend to ask some random person like Jan, could you give me an example? IoT. That's a great example. But let me ask you slightly differently. How often do you charge your phones, like mobile phones, smartphones, whatever? Do you charge them once a week? Who charges the phones once a week? Raise your hand. Who charges your phones once every 3 days? Oh, we have 3 people. Yeah, I assume you use it moderately. Who charges their phones every 2 days? Yeah, we have a bit more people, about 10 people in the room. Who charges their phone once a day? We have like 80% of the group. And who charges it more often than once a day? And we have some also probably phone addicts, like myself. So if I were to promise you an awesome app on your phone that will provide some fireworks functionality, would you be willing to install it if I tell you that it drains your phone battery 3 times faster? I don't think so, because it simply decreases my life convenience, right? I would have to charge my phone 3 times more often, which, counting it, would be like more than once a day, so pretty terrible situation. Yeah, but if you're wondering, apps like this for laptop, for example, exist. And with consuming lots of energy, they also fortunately heat our houses by heating the processors. But actually, energy consumption does not only matter there. Here I have gathered some statistics about Microsoft, Google, and Meta, which was till recently called Facebook, so I will refer to it Meta, aka Facebook. And you can see that if we recalculate how much energy they have consumed running their projects, all sorts of them, you could actually equivalently power about 3 million of people just by the power that was used, just by the energy that was used by Google itself. So even if they are able to introduce a small change in their energy consumption, like small improvement in their energy consumption, in the scale at which they work, it introduces great improvement. So why does it matter? The motivation may be very different. We might want to save on the bills, like imagine that Google can introduce new programming language like they do from time to time, and the next one will actually save on some energy power, possibly. So they can decrease their bills, right? You can be concerned about environment, and here I have a screenshot of an article about the company that was actually buying a power plant to power their Bitcoin mining stuff. The issue there was that the power plant was actually running on coal, so debatefully it was not the most environment-friendly thing. And yeah, among other reasons, environment is also something we should be concerned about, probably. So what should we do to save electrical energy? And yeah, we can go full Amish mode. Give up everything make a step back 200 years ago, right? And I don't want to make jokes about Amish. They are great people. They handle without electricity. That's like an extreme challenge for me. I mean, I don't even know what the date is if I wake up in the morning. I am slightly sleepy. I have to, log in, and I don't know if it's Friday or Saturday, so should I log in to work or not? Which, by the way, also has to, for which I also have to use electricity, right? So yeah. So to be honest, we can assume that for relatively possible things, it will be very hard, if not impossible, for most of us to switch to the pre-electric era, right? Yeah, and by the way, if I inspire any single person to switch to becoming Amish, I would love to do the very last thing they do with electricity is, let me go back. Yeah, email me. That's the last thing I want you to do. Please, please. Okay, so let's be reasonable now. We could use more efficient technologies. So if you think of back in the old days, they used to use carts with horses to transport stuff or ships. Then they switched to steam power, right? And steam power introduced completely new branches of, possibilities thanks to the relative power that it could give. The next step was switching to combustion engines, and yet the next step was switching to electricity, which again, when transferring energy, gives us much, much better efficiency because of smaller losses, right? So I don't want to dive into numbers, because who likes numbers at the second day of conference right after the coffee break? Yeah, so let's start from understanding what the problem is. What the electrical current is? Well, you have the definition from Wikipedia on the slide, but quite frankly, it does not really tell us much, right? I would like you to think about electricity as a magical power that provides us certain possibilities, from powering light bulbs, and I know light bulbs are pretty old-fashioned nowadays. We should say LED lights, right? Because that's what we nowadays use. But powering from light bulbs through our laptop servers, even this projector, all the way up to the lightnings in the Thunderbolt, right? So this is the magical thing powering lots of things around the world. So there is much more reasonable explanation where we don't have to know much of physical data, and we can understand basic terms of electricity. So on the picture, you have three guys. First one is the yellow one. It is the voltage. And voltage is how willing electrical current is to move. The higher the voltage, the more the yellow guy is eager to push the green guy, right? And the voltage is passed in volts, and I have a small gadget here. I don't know if the remote audience, unfortunately, will not be able to see that. This is an AA battery, and I can hold it in my fingers at both ends without being terribly electrified and dying from that. This provides between 1.2 and 1.5 volts, and coming slightly back in the time, or in the slides, if you think of lightning in a thunderstorm, it provides lots of thousands, if not millions of volts. I think it was not even measured just yet how big the voltage is there, but it is big enough that it actually manages to make air, which in normal conditions is isolator, it manages to make it into conductor, right? So this must be great voltage, extreme numbers. Yeah, so we've discussed the voltage. Now we have amperage. Amperage is how much electrical current goes. So this is the green guy trying to squeeze through the pipe. And we have ohm, which is representing electrical resistance. This is the least important thing, just so that you're aware. Resistance is how difficult it is for electrical current to flow. Yeah. So being able to operate with those actually two terms, because we'll mostly be using voltage and amperage. So we will say about the current when I say amperage, because it's in amps. We'll be able to describe how much electrical energy we use. Right. So the term that we have is how much electrical energy we use in every single moment is power. And here comes extremely complicated mathematics at about level of, I think, second or third grade of primary school. So there is, again, definition from Wikipedia, but what matters here is that the power of each device is, we just have to measure how much current flows through it when it runs, and under what voltage it works. If we measure those two values, multiply them together, we get how much power it uses. And this is something that you very often can see. So if you, for example, buy a kettle to drink tea, or I assume most of you drink coffee, then you will see on this small metal piece of board that no one reads that it says how much power it consumes, right? So going even further into the maths, we have energy. And energy is simply power consumed in time. So if my kettle that I mentioned in my previous example, so it's still the same one, right? Runs for 2 hours, which is extremely terrible cattle to make the tea, because who will reasonably wait for 2 hours to make some tea? And it consumes 1,000 watts of hour, 1,000 watts of energy. I may say that it consumes 2 watt hours of energy, and I will be referring. Obviously, the energy unit is watts. Sorry, energy unit is joules, but I will be referring to energy unit as kilowatt hours or watt hours, simply because this is how it is done in the industry. And if you get the electrical current bill, you will have the energy passed there in the kilowatt hours. On slide, you have simple calculator how to recalculate kilowatt hour into joules, or in this case, megajoules. So this is millions of joules, right? And the most important thing on the slide, this is about as hard the math gets on the stock. So I almost promised no harder maths. I hope you are with me. Yeah, so now from knowing all of this theory, you have to go to the practice. And I have this awesome picture prepared. So I've decided to set up some hardware setup where I have a full rack of servers, which in my case is a single Raspberry Pi. So you can see that there is some power there, right? Google, I'm coming. This is powered separately through. This is powered separately through this nice green square. This nice green square represents a sensor. In my case, it was sensor INA3221. And I am sure that you all know this board very well, but just in case someone forgets, this board is, yeah, this was a joke, so feel free to laugh. Just so that we are on the same page. This board, what it does, you power it, and you put the power supplies through it, and it allows you to read the measurement of what voltage is passed and how much current goes through it. So I can relatively well tell how much my Raspberry Pi consumes power. Now this reports to my another server, which in this case is Arduino connected to another Raspberry Pi. So you can see that AWS, brace yourselves. It just reports the data over the I2C protocol, which is then processed through Arduino, and then it is forwarded to the second Raspberry Pi over the serial port, because this was the simplest and most naive implementation I could possibly do, and also possibly no bugs there. Yeah, and then this data is sent further to some database to be stored, and on this nice blue monitor, you can see some awesome graph of actual power consumption, which was just a random graphic from the internet. In my case, I was using Prometheus and Grafana to display the data, to collect and display the data. And the important thing here is that this technology is almost good for this use case, because the Prometheus is actually pulling the data, the data is not pushed to it, which means that the rate is, on one hand, there is like back pressure on the rate of pulling the data, but on the other hand, you cannot have as high sampling rates as you might have with pushing the data. Yeah, and the last thing on this graph to be explained, or last but one thing, the red arrows are actually requests for my simulated clients, which we'll explain later. And yeah, why there are 3 zips on the top? Each zip represents a separate power supply. This is relatively important or pretty much important, that there is a separate power supply for the tested device and for the rest. So how many are there? It doesn't matter. It matters that this is separate. Yeah, so from theory to practice. So if you remember the MasterCard commercial, there were some priceless things. I've learned the day I've started setting this thing up, I've seen one new priceless thing. It was my girlfriend's face that she entered the house and saw all of this stuff on the kitchen table. So yeah, next day it was all cleaned up, just so we are on the same page. And I moved all of the computers to the drawer. There is actually extra benefit to the drawer. It has relatively stable temperatures, so all of the tests have relatively the same values. Because if I open the window, then the temperature in the room changes, and this may affect the results of which I measure. This is also why the relatively new MacBooks actually were so well performing in the fridges, but I don't see many developers so keen on sitting in the fridges all the time. So yeah, if you are in the electricity topic, there's another funny thing, because you may suffer from the Wi-Fi issues in the fridge, because the fridge is mostly covered with steel sheet. That's why you might be in the Faraday's cage. So the Wi-Fi is poor there. That's why probably they are not there, right? Otherwise, all of the yogurts and stuff doesn't matter, right? Yeah, so I decided, so having the hardware set up and running, how hard it was, right? Or how easy it was. I decided to create some benchmark, and here I encountered a certain problem. What kind of thing I want to measure? What kind of benchmark should I design? And on the slide you have some of the assumptions. The most important one, and kindly hidden one, is the easy to implement thing. But also I wanted my program to be relatively representative on what kind of programs do we write today. But if I tend to ask a certain person, so if I tend to ask, for example, Jacek, so what kind of programs do you write on daily basis? And I know that Jacek is working for a bank, so he will tell me, I obviously write all sorts of bank applications, right? If I ask some other person working some other stuff, they will obviously tell me what they do on daily basis, but how is it representative for the whole industry? It not really is. Although there is one thing that we all have in common. We all are sort of happy with new technologies, right? So one of the things that we are moving towards is, from having this huge monolithic applications, we are slowly moving to microservices, and microservices is the great boom, or it was a few years ago. So back to the future. Never mind. I decided my application to be microservice. I wanted to have it simple, so it is extremely simple HTTP server that just accepts this JSON request on the top and multiplies to matrices and then returns the result. I also included the length. The length is the how many columns are in the matrix, and the height is how many rows are there. This was just because I assumed there might be some crazy programming language that it will be difficult to do this maths in, but it turned out it was not used at all, so fun times. Yeah, so basically what the service will do, it will have some sort of HTTP server. The HTTP server will accept the JSON. You need to decode this JSON. After you decode this JSON, you need to multiply those two matrices, which is much more algorithmical task, and then pack it up together. So you encode and you send some kind of response, right? And that's it. And I managed to do it for, yeah, so here are some of the results. So the one on the top left is Erlang. The one on the top right is Node.js. The one on the left bottom is Python, and the one on the bottom right is Ruby. And I picked those four because they are extremely different from each other. And also, the cool part is you can see that there are completely different ways of handling certain requests. And I assume that you don't see those small numbers in this, on the axis, but basically the vertical axis is the power in watts. Yeah, it must be watt hours probably, or no, it's correct. Sorry, and yeah, and the horizontal line is time in seconds. You probably can't see that, but there are different times of execution of each of the benchmarks, and just to explain, each of the programs I have written was given the same number of requests. They were all given 10,000 HTTP requests to handle with matrices of size anywhere between 20 and 100, both in height and length. And is there any more notes to be there? Yes, so the relatively important note and observation from those graphs having different times of execution is that I should not be using the fixed time window to calculate the power consumption, but I should rather be using the fixed number of requests simply because the time executions are different. So by the time Ruby would be able to handle certain number of requests, for example, Python would be able to handle a bigger or smaller number, which actually represents different type of work, right? In terms of what we get there. I think the interesting thing here is the patterns that occur. So this one is the most interesting for me. This is the Ruby implementation. And I am complete noob in Ruby, so there probably is some kind of weird thing that I did wrong. But the pattern emerged because Ruby was able to consume 50 requests a time. It somehow probably processed them so it gave up on accepting any more requests. It processed them, returned the answer, and only then processed the next 50 ones. So this is why this funny pattern emerges. Yeah, so that's probably the most interesting pattern. And I ended up running the benchmark for 5 programming languages, and there were more of them, but I decided to discourage some of the results because some of them were pretty hacky, some of them were very hacky, and some of them simply didn't work or had some flaws. So I ended up giving those 5s. And the thing I'm most happy about this statistic is that Erlang is actually not the first one. And why is that? You may say, yeah, you are an Erlang developer. You should be writing the code that's the best when comparison to other programming languages. And this would be the case, but this would suggest that the result would be then biased, because it would mean that I have actually used my Erlang skills to write better programs than in other programming languages and technologies that I'm relatively newbie in, right? So the Erlang being not so much on the top of this list, saying that I actually did a good job of being fair with relative comparison. And yeah, one more note there. So you see the Ruby is much, much worse at the end of the list. This is because, as I told you, it was consuming 50 requests at a time, processing them, sending response, and so on. And in Erlang, it is slightly worse than others because in slightly naive, yeah, I'm politely saying slightly. I understand you're being upset. Because in other implementations, I actually use array accesses, so this is instantaneous. And in Erlang implementation that I have politely copied from Stack Overflow, the second matrix, so if we go slide back, this B matrix actually gets rotated, so we have access to the column as a list, and only then the row from the A matrix and the column that was reversed, that was rotated from the B matrix gets zipped and multiplied. So this actually requires a bit more operations than in the other implementations. So this is probably, I would say, implementation detail, but the one that made the difference. Yeah, but you may say, so these are only 5 programming languages. It's pretty poor, right? So which one should I choose, right? Maybe there's some better one. Maybe there is the most efficient programming language across all of them. And there is a great paper. I've posted the title and all the authors. They are from 3 Portuguese universities, if I counted correctly. And they managed to run, I think it was 12 or 13 benchmarks for 27 programming languages. And here, for all conspiracy theorists, if you notice that I have provided 5 benchmarks, they have provided 27. Each of those numbers is actually perfect number -1. Perfect number is like 6, 28, and so on. It's the number that, I know I promised no more maths, but this one is actually interesting. The perfect number is the number that is sum of its own dividers, but not including itself. So 6 is divided by 1, 2, 3, and 6, right? And if you sum 1 plus 2 plus 3, it gives 6. The same happens for 28 and so on. So no conspiracy between us, me and the Portuguese people. So here are the results for 3 of their benchmarks regarding energy consumption. You can see they have n-body problem. N-body is simulating something like solar system that you have bodies somewhere in space and they interact with gravity and so on. The detailed descriptions of each of the papers are done in their, each of the problems is done in their paper. There's fast A, which is generating DNA sequences, and there is binary trees, which is creating, traversing, and deleting binary trees. You can see that actually in those three, Rust is on the top of two of them. If you go through all of the researched ones, C will most likely be the one at the top. And here are the most interesting conclusions. They actually, if we go back to the title, they actually compared three things. They compared energy consumption, time of execution, and memory efficiency. And it turned out that you might suspect that time correlates with the energy efficiency. It mostly does, but not always. But when it comes to memory, the patterns might be completely crazy. And these are the results I have placed here. So when it comes overall, when it comes to the how those programming languages show up in this energy efficiency, you can see a pretty reoccurring pattern that compiled programming languages are those like the cyclists escaping from the peloton. Then the main group is the VM machines. Sometimes Java is trying to catch the escape group with their VM. And then you have interpreted languages somewhere on the start that they simply broke their tires, right? So they are probably not the most efficient one. And overall, the most expected probably question of all the talk is that C has won the energy efficiency race. And we have Mr. Linus Torvalds laughing. For those of you who don't know the person, he is Linux creator. That's one note. And the second one, he is kind of in favor of C. That's why I posted him. And on the very next slide, sorry. Is it all about efficiency, Mr. Torvalds? Well, no. Here you have the very inspiring quote I found about Lua, which basically says that Lua is a very good programming language simply because it does not try to solve the stuff that C already solved. And let me ask you this: would you give up HTTPS over HTTP because it's more energy efficient? I wouldn't, especially when it comes to connecting to my bank account, right? Or there is someone who could, please raise your hand. I'm very willing to talk to you after the talk. I'm even keen on borrowing the laptop to, give you the access to. Never mind. Unfortunately, no hands raised. I'm not sure I follow. I'm rather sure I don't follow.
I've meant that there are many video games, online video games, that have very strict anti-cheating systems, and they're often written in C++, which was on the top of the most list. So maybe sometimes you don't have to give up the quality.
Yeah, so in this case, we have three lists. There were actually like 12 or 13 benchmarks, and C++ is somewhere on the top, right? So yes, that's probably one of the more efficient ones. Now, quite frankly, there are actually a few more questions. So would you be willing to give, for the Haskell developers, are there any? Not many. Yeah, we have 1, 2, 3, like 5 of them. Would you be willing to give up your static type system, your monads, all the fireworks Haskell provides for energy efficiency? Yeah, I can see them nodding, or I hope I can see them nodding. Yeah, they are not willing to do so. For the Erlang developers, and I have a few here on the classroom, I can see them by their nice polos from Erlang Solutions and other companies as well. Would you be willing to give up supervision trees, all of the reliability, the built-in distribution, the debugging skills, the tracing stuff, all of that provided by OTP, and so on, for energy efficiency? Who is willing to raise your hands? I can see no hand on the room. Right, and the same comes with me. I'm not willing to give up that. And I could probably ask the same thing about Scala and F#, but unfortunately I don't know much enough stuff to mention those cool names that come with the languages. But still, the same rule applies. And yeah, actually, I don't think it's the way to go. Here we have an example of Facebook Messenger. This is the whole akapit because it only made sense in this way. I couldn't really cut the sentences out of context, or it would not make head nor tail for you. When they were implementing Messenger, back then it was Facebook, now it's Meta, they actually decided to use MQTT, even though they tried other solutions earlier, to save on battery energy consumption from battery on phones. And why MQTT, you may ask? And this is a great question. Thank you for asking that, Alexander. So MQTT was used because this is a protocol that is designed to be efficiency with the bandwidth that you have and to be efficient in terms of electricity consumption. It is designed to work with all sorts of sensors, probes, stuff like that. And that's why they decided to use this protocol, which is from completely different space, into connecting to our phones, right? So whoever uses Messenger, they can probably see this MQTT communication if they attempt to do so through Wireshark. How are you on time? Yeah, and the second inspiration here is, this is a tweet from, as he introduces himself, the head of WhatsApp. This, just to give you a little bit of context, a few days later, Erlang introduced new OTP version. And this new OTP version included just-in-time compiler. What they did not change a single line in their code. But what they did instead was recompiling and running their code on new version of Erlang, including this JIT, this just-in-time compiler. And as you can see, they claim they have managed to save 25% of their power they have managed to save 25% of the power they consume with just this minor change. And I actually am privileged to talk to people who create programming languages, who create all sorts of compilers, stuff like that. I would like, since I am just a not so humble programmer, I would like to ask you to do your best and create the best programs you can, the best programming languages and technologies you can, so that we, the not so humble programmers, can use them efficiently. And this is the message for my talk. Thank you very much. If there's time, we can have some questions.
Thank you, Alexander. Now we have time for Q&A. So questions. Do you have any questions in the room?
Yeah, I don't know if you are stunned or I'm so boring that you don't want to ask me any questions, not to keep me talking. So.
Okay.
Great talk, thanks. Just was curious when you showed the chart with all three of the, sorry.
The chart.
With all three of the, yeah, this one. I can see there are some arrows next to each language, almost all languages. So do you know their meaning or?
Yeah, the arrows are actually referring to, what the changes were to, I think, because in the main, these are the screenshots. So in the main paper, I think they sum up like standardized results of all the benchmarks. Sorry, not all the benchmarks, but most of them, because some are runnable only for a certain subgroup of programs or programming technologies, and therefore they show how it changes in particular benchmark with relative to all the benchmarks summed up. So this is the meaning of the arrows.
Okay, any more questions?
Please turn on the mic.
No, sorry. Do you have any information how power consumption is related to language features? For instance, garbage collection costs so much and something else.
Do you mind explaining the question slightly further, because I'm not sure I follow.
Yeah. Can you say something about the energy cost of particular language features, for instance, garbage collection?
Well, regarding the garbage collection, I assume it costs something because that's what was shown through this idea of having compiled languages, then having the VMs, and only somewhere at the end having the interpreted ones. But I assume you can make it work relatively well, which was the example of JVM actually trying to catch up with the compiled languages, right? So this is it, and I'm afraid it's not so difficult to find any pattern emerging that, yeah, you have certain feature and this actually makes your program this and this percentage better in terms of energy consumption, or this worse. I assume that if your programming language is interpreted, then there's an issue. And also I was looking for correlation if certain pattern emerges if I pick, for example, functional versus object-oriented versus procedural, and I was unable to find any reasonable patterns there. So there might be there. I am not statistician. Even if I were, I still could have missed them. But long story short, I did not find any significant patterns.
Do you know whether in this study that you presented, whether the authors used any libraries, or were they just comparing the standard language runtime, or whether they
That's
were
a very
testing?
good question, and this is actually something that I think is worth considering to rerun, because they were running that like 6 years ago or so, I think. So if I think of terms of Erlang, that was Erlang 19. And yeah, if you go to nowadays, we have this just-in-time compiler, right? They have actually added some extra results for Julia, I think, but that's to be looked up on their website. They have very cool website. So extra results about Julia on their websites from 2020. And yeah, the 2 years in computer science is quite a lot, right? They actually have used the programs that were implemented in something, they name it. There is like a game of implementations of those problems, and they have taken they were not running it by themselves. They were taking it from there. Yeah, and in my case, I am extremely lazy person as a programmer, which I was told is a good thing. So Joanna, forgive me. Just for the context, Joanna is my boss. And yeah, in my benchmark, I was actually lazy enough to use some libraries. For example, in Python, I was using NumPy to multiply the matrices. And in Erlang, I wanted to be extremely fair. And there is a concept that you can actually use C calls inside Erlang, which is called nifs. And I could have done that at 2 points. One is decoding/encoding JSON, and the second one is multiplying the matrices. And I decided to go pure Erlang, just to be fair. So this is also a reason why, if I were to do it, I would probably get the reasonable results like Python in Erlang implementation, right? So does that answer your question? I hope so.
Hi, great talk, thank you. And do you think the Lua approach could be a good one? That is, should we invest in interoperability and use some of those languages from the top of the list for something we identify as the most resources heavy?
Yeah, so as I just mentioned, this is exactly the approach in nifs, right? You can delegate some very algorithmical stuff to, this is actually Erlang specific, right? You can delegate some stuff like multiplying matrices to run, or decoding JSON to run in C, and only then play with this very nice structure in Erlang, getting this nice stuff there. So I assume that's a nice way to go. Also, if you look at Python, that's why Python is so popular in terms of artificial intelligence, right? Underneath, I don't think they are running pure Python. If they were, they would still be evaluating this very first neural network they started. Right? So.
Okay, any more questions? I think that's it. So let's give another warm round of applause to Aleksander for his great talk.